So, hi everyone, my name is Matt, and I wanted to record a talk I did a little while back about self-supervised learning, in particular the ideas and how they relate to the sort of use of large unlabeled datasets. So, this talk, I guess, in some ways is really about representation learning and how we can make use of that. And I'm going to basically think about these models we build as being these functions f that generally sort of go from input on the left, that's this x, to some output on the right, which is y. And we're going to use this x and y pretty much through this talk. So the goal of any sort of learning is to learn this function f. Often on labeled data, that's why we often start with pairs of x and y where we know the answer, and we sort of want to allow a model to learn some generalized version of that, so that when we get a new x we don't know the y for, we can sort of predict it. Now, I think what's generally the case with these sort of models, which is of interest, is this idea that in some way that these functions sort of takes an input, which is usually quite high dimensional, and sort of does a prediction on it, which is often lower dimensional. Now, I say often because it's not always the case, but even in those cases where it's not, a model often has this idea of some sort of compression, some sort of idea of a bottleneck. So the y may be quite small, like a extreme version of this. We might have a y like some number of categories, and the x is a very high dimensional thing like an image. Now, of interest around neural networks is this idea that the f usually isn't this direct mapping. What we end up getting is f is sort of decomposed into lots of little mappings, and this can be like what we think about it as layers or some modules, depending on how we're building things. And so really there's multiple f's that all get learnt in parallel, and each one's sort of responsible from taking this input and making some change to it to learn a representation, and then another change, another representation, and eventually to our target that we're trying to predict. Now, this talk, I want to sort of talk about particular intermediate representation. I'm going to call this E. This is like an encoding. So as we're learning this model, we're sort of going from this X through this sort of compression and sort of slight modification again and again and again until we get this representation that eventually gets to our prediction. And I want to call out one of these intermediate layers that's more towards the right hand side, so to speak, so closer to the output than the input. And one thing that's useful really around this representation is we can often relearn and reuse this representation. And by that I mean the following. So we sort of start with this x and y, and we can think about these two parts as actually being sort of separate models. There's everything up to the e, and then from the e to the y. So we sort of, in some way, you can think about training two models at the same time. And the loss of this model relates to the true value of the y and this predicted value of the y hat. So our loss in some ways is this function of these two, but these models we can think about as training together. So we're sort of jointly training these two things together, this intermediate E. Now this is useful in lots of different ways, and one of the ways that's really standardly known is this idea called transfer learning. What we do in transfer learning is we start with an X and a Y, which is really big. That's what this B stands for. Really, really big sort of set of data. And we sort of do this mapping and we do these predictions to a very big set of predictions. And because this data set is very large, this model is often very large. So this part of the model is large, and the whole thing end to end is large. But remember that I talked about this idea that because this E that we've chosen to look at is sort of more towards the right-hand side than the left-hand side, if we think about these two models, there's a lot more parameters in this part of the model. So if we have to think about this as being two models, this model is quite large and this one is quite a bit smaller. And what's of interest around this is that this model in some ways can be reused, and in sort of the following way. If I take a small data set, so I've got an X and Y now that is a small data set, and these X's are somehow the same. So by that I mean, like, say this was a bunch of images that were taken from a standard phone camera or something. If I have some more images that were also taken from a phone camera, then what this model has jointly learnt in the goal of predicting this Y is these intermediate representations, which possibly are useful for my problem too, because they sort of relate this mapping from this X to this Y. And if my X's are similar, then depending on what my Y's look like, if they're sort of sort of roughly the same, you know, in terms of what it's trying to represent, there's a good chance that I can reuse this first part of this model. So if I'm reusing it, that's actually a really good thing, because there's generally this idea that the larger and more complicated the problem, the larger the model is required, and the more complicated the model in terms of its sort of size, the more parameters it has, and the more parameters it has, the more instances of sort of training examples are required. So if I'm able to reuse this part of the model, then all I'm really responsible is for training the second part. And if we talked about this idea that this part, the left-hand side, this encoder had a lot of parameters, by reusing the encoder, I'm saying that I only need to train a small amount of parameters. So if I'm only training a smaller amount of parameters, then I don't need as many examples. And you can sort of see how this makes sense in terms of what is the encoder's job. If you think about that funnel again, it's about sort of taking this very high dimensional data and sort of in some way compressing it to much lower sort of dimensional representation. And that lower representation sort of captures some essence of this original data set that's more like this prediction. So by reusing this E, I can say that I don't need as many parameters, so to speak. And so this is always a really handy thing if we can get away with it. So let's think about the same idea then, but instead of a big and a large one, let's think about an unlabeled dataset, so a very large unlabeled dataset, and a much smaller labeled dataset. So I want to be able to reuse the same idea, that somehow when I've got a large unlabeled dataset, I can sort of learn some encoders that I can reuse. So I want to follow this same sort of pattern. I want to say that I'm going to train these two models jointly, and then I'm going to reuse this part for the purpose of only having to train this second part. The whole problem is, though, is that I don't have these labels. These labels here don't exist. So I'm not able to do this top part because I don't have them. So my intention is to want to do this sort of thing, to train this large model so I can reuse it, but I don't have the label. So what are we going to do? We have to be a bit clever about what it means to have these labels. Just as a side, as a bit of a rant, I mainly say this is a rant because I've seen a couple of people in papers talk about this recently, even though it's a really old idea. And, you know, so I just want to go through something really quickly. If I do have this type of problem, where I have some really large unlabeled data set and a large labeled data set, one thing to try first is this idea of self-training. It's very simple. What we start with is we train a model on our labeled data set to predict this Y from our true set of Ys that we know. And then what we do is we use this model that we've trained on the labeled data set to label through, you know, some prediction, the unlabeled data set. What this gives us now is effectively a form of labeling of these unlabeled data sets that we can actually union together with our labeled data set to retrain on. Now, this at first glance seems a bit strange. It seems a bit like cheating to say that we can train a model over here and then use that in application and then just sort of union things together and get a bump. But it actually does work very, very well. And this is a technique that's been around for a long time, and certainly encourage people to try it and give it a go. So that's self-training rant over. I wanted to go back to self-labeling, or, you know, introduce self-labeling. I think it's the first time actually, and I want to start with one of the most fundamental, I think, well-known ideas in self-labeling, which is this idea of doing things from sequencing. And I want to talk first about this example, classic example called language modeling. Let cats out on the blank. You know, what is the blank? And when we talk about learning models for this sort of stuff, it's generally called language modeling. And I think language modeling is, in some ways, the most successful example of self-labeling from sequences. And this is all we have to do, basically, to self-label in these sort of cases. Is we start with a large corpora of whatever, you know, copy of the internet or whatever we might have lying around. Cat sat on the mat by the window. And what we do is we actually sort of, from this structure, we make our own set of labels. So if we're interested in predicting the next token from a sequence, then we might do something like this. The cat sat on the Y. Well, that's one instance of training. We can say this is a one instance. And then we basically just move the window along. So here's another instance. Cat sat on the, what's the next word, mat? Sat on the mat, what's the next word, by? What's the next word, by? So by using this sliding window approach, we can actually just sort of generate a whole bunch of labeled data, and we call this self-labeling because it's sort of part of this data set describes not just the X but the Y as well. And this idea of sort of learning some sort of model or encoder that takes some tokens and sort of predicts other tokens nearby is like fundamental to almost all of NLP. This is how these models are built. For different versions of what you think of as the left-hand, right-hand side here, contributes most of natural language processing in neural networks for some time. Very big results, often built around this whole premise of self-labeling from a large data set. And a couple of arguments I get into people about, is this unsupervised, is it supervised, is it self-labeled? It's a fun thing to talk about. So another way that you can do this sort of self-labeling, which is around trying to use structure to make labeled data that you can then treat as a supervised problem, is around contrast. And I think these are really, really interesting cases that I'm going to just take off more and more and more. So let's think again about this original problem where we had some sort of XY pairs in our data set, and we're using again these two models. We're sort of thinking about the two models in one. That we're, through this X and this internal encoding, we're going to predict a Y. So let's, and I, this subscript I in this case just talks about one particular example. And again, in the supervised case, what we do is we sort of talk about the loss objective being related to the true Y and the predicted Y. Let's think about also another example from the data set, the Jth example. So again, we've got the same sort of idea that like XY pair, the Jth pair, that goes through some encoding and from that makes a prediction about the Jth element. So one thing that's really interesting to think about here is that if I was careful in choosing my I and J here in terms of the data set, and I chose an I and J such that the Yi and the Yj were of the same class. So say we're doing, n-way prediction or something. If I chose the I and J so that they were the same class, then we'd want these two functions that we're learning to predict the same thing, because they are the same class. So if these two are the same in terms of what we want the predictions to be, then there's rough statements we can make around smoothness that says that these E's, these intermediate representations, especially the ones closer to the end, should also be the same. Well, and it's a bit fuzzy here what it means to be the same. They can't just be the same, otherwise there'd be no interesting generalization of the network. But they should be more similar maybe than other very, very different I and J's. And it's a bit of a fuzzy statement, but the main crux of that statement is that I can make a bit of an assertion like that these encodings should be like each other in double quotes, under this idea that the labels are the same without knowing exactly what the labels are. So for any pair of labels that are the same, without knowing that they are, all I need to know is that they are the same. And that's a really interesting difference in constraint. I don't need to know what they are, I just need to know that they're the same, because that allows us to represent pairs of these sort of things in a very different way. So one way that we use this sort of idea a lot, this idea of things being the same, is actually in image augmentation. So here's a thing we really classically do, or not just image augmentation, or augmentation actually. It's a classic thing we do during training time. So here's an example of an image that I took from a little robot simulator called PyBullet, that, a robot arm doing some stuff with some things in a tray. There's a really classic idea that says that if I'm doing something about this image in some sort of, maybe I'm doing classification, 5-way classification, something about this image, then one thing we do often is to say, is there changes we can make to this image in pixel space? Things like, small rotation or crop, a brightness or contrast change. Is there small things that we can do that don't change the label? And so, rotations, small crops, translations, classic things. And the reason we want to be able to do these things is because it makes more examples for us to train on. Basically, if we do this image augmentation, then effectively this permuting of the X a little bit around the things that should be invariant to the class change. And this is something we always do because it makes things much more robust. So this idea of image augmentation is a case of a function that when we apply it to a model, oh sorry, to an input, piece of input, doesn't change the label. That's you know, and for text and for audio, there are lots of equivalent things, but images are ones that I think are really easy to think about. So we can actually use this image augmentation in an interesting way relating to that last point I made about things wanting to be the same. So say we do the following. Say I take an image, X, and I augment it twice. So I've done one augmentation, another augmentation. So, you know, maybe this has rotated the image and changed the color a bit, and this is a different rotation and a different color change of the image. When I run this through my first part of my network, this encoding part of the network, I should get some encodings. Now, under this idea that the encoding should be the same for the classes not changing, and the idea that image augmentation doesn't change the classes, I can sort of treat this part of training the encoding under this idea of image augmentation of saying that when I've augmented these two images, when I've augmented this image to get these two, I don't want these encodings to change very much. So I'm gonna introduce a loss function that talks about minimizing the distance between these two for this specially chosen thing. Now you can see here there's no y involved in this. I don't have a y like we traditionally did. All I'm doing is saying I want to learn an encoder that basically is robust to the type of image augmentation I talked about. And why do we want to do that? Is because of that idea I said around if image augmentation doesn't change a label, then I can learn this encoder, which for this image augmentation doesn't change things. And this may be a good encoder to use for my other case where I had a small amount of data, because now this image encoder has sort of learnt something interesting about the compression from this very high dimensional space to a much, much lower dimensional space, where things that are nearby in this space, this encoded sort of space, already represent something fundamental about the class of the objects. Now I need to be careful here because one way of minimizing this distance between these two things is just to map everything to 0. So, you know, the degenerate form of these things, the optimizer will certainly find very quickly. So I don't want things to be totally, I don't want everything just to map to 0 as a way of minimizing this. So we have to be a little bit careful. What we often do is we'll pull another element, another random element out of our training set. We'll also augment it. And then we'll say that this objective here is not just around these first two being close, but the first and the third being far apart. So this is a classic loss that we've used in lots of cases. Lots of metric learning uses this idea of that goes by a triplet loss, where there's two things we want to pull together and there's two things we want to push apart. And you can really imagine here that under this sort of idea of depending on what this image augmentation is, you know, because it sort of really is conditional on what this image augmentation is doing, this embedding starts to learn a good set of representations for this input, such that as you augment the images in different ways, you sort of you keep the images or the embedded version of the images close to each other. And this now, because it's a much, much lower dimensional space, this space of the encoded space, means that when we're doing some training on this for another task, we can get away with a much smaller model. Now, it's all very, very based and conditioned on what sort of augmentation you're doing here. So a lot of work has been sort of looked into what sort of things do we need to do here, because this model will only be as robust as the image augmentation is. So lots of people have been doing lots of different stuff with this. Often things that in terms of image augmentation are more aggressive than we would normally do with image augmentation. So very aggressive crops within crops that don't overlap, for example. Things that maybe in the cases that we would use for like image classification would be too strong. They would be too strong in terms of breaking sort of classes. So image augmentation now is this idea of using image augmentation to learn an encoder for embeddings is very common. I think there's actually more interesting ones though. Here's one that I think the first one that actually got me into the whole metric learning and really interested in it. This is it comes from a result called time contrastive networks. So again, what we're looking for is this idea about what are some examples of images that we can pair up to say these should be sort of encoded or embedded into the same place, whereas others should not. This is a really cool one. I think it's fascinating. I'm gonna, instead of looking at one image of a robot arm doing some stuff, I'm gonna actually consider a video camera, so a video feed of images. So here's a view of a camera, And you can see the arm here, it's just sort of reaching into the tray. Maybe it's sort of picking something up and then it's going back up again. And from left to right is some sort of idea of time. This is one view, but one thing we can do that's really interesting is we can actually take another view of that same scene and sort of at the same time, but from a different camera angle. So again, from left to right here, each column here is the same time, but from a different angle. We can see the arm sort of reaching down here. This is where it's sort of touching the stuff, and then it's reaching back up. So we have two views of the camera. Sorry, two cameras viewing this robot arm over time. And it's really interesting because we can use these two sort of views to build up those examples we talked about in terms of what's going to give signal to learn a really interesting embedding. So let's consider a problem that relates the wanting to predict something about the pose of the arm. And so the pose of the arm is, basically the description of all the joints, so to speak. So this is a 7 degree of freedom arm. So the position of this arm, with the rotations and angles is defined by 7 points. If we think about a particular point in time, like these two green circled examples, then the pose of the arm should be the same. So even though the pixels look very different, we know that the arm, because it's at the same time, has the same pose. Now let's think about these two examples. These are examples where this is a bit of a hard assumption always to make, but if we make the assumption that the arm is always moving, then these two images, we expect the pose to be different because the robot arm is always moving, even though in some ways these red images are more like each other than the green ones. So what if we were to use these pairings as a signal for learning this type of embedding? These two, the green ones here would be the cases where we want the embedding to be the same. So we're saying that when you embed this one and this one, we want the embeddings to be the same. We want the output of that network to be the same. And for these red ones, this one, we're saying we want the embedding to be different. This is actually quite difficult when you think about what's happening here, because the two that we want to be the same actually look quite different in pixel space. They look quite different because it's a slightly different angle. Whereas the ones that we want to be different actually in pixel space look very similar. And if we think about this a little bit more, if we want these two embeddings to be different, or more different than these other ones, and we want to sort of maximize the distance between these two, but minimize them in this space. If you think about these two, for the most part, the scene looks pretty much the same. The tray and the objects all look the same. So using this as an objective means that the network that's doing this embedding needs to really focus on the arm, because that's the only thing that's not changing. It really needs to understand that the contribution of the tray and the objects doesn't contribute anything to the embedding in terms of wanting to make these different. So this is really fascinating. I think it's a great example of how we can use this idea about some sort of invariant we know we want to hold, this idea that these two should be the same because they're taken at the same time, because time is, any two pictures taken at the same time should be the same, whereas these two over time are different. We've got a lot of flexibility about how difficult we want to make this too. You can imagine that these two cases where you've got the camera the same, depending on how far apart the cameras are, we can make this harder or easier. If we're saying we want these two green ones to be the same and the cameras are right next to each other, then they would be quite similar in pixel space already. But as we move the cameras further and further apart, even though we want them to stay the same, the pixels change more and more and more and more. So it's like a form of difficulty. We can sort of anneal difficulty by, in terms of this positive case, we want things to be the same by making the cameras a different sort of angles from each other. Same sort of goes actually for these negative cases, the cases where we want things to be different, because you can imagine the closer and closer in time these two are, the harder and harder it becomes because the arm has moved less and less. So the further in time you sort of wait to pick this one that you want to be different, the easier it's going to be because there's more chance that pixels have changed. Whereas if you were to take this red example here as the next frame, it would be a lot harder because most of the time things haven't moved very much. So this idea of contrasting something over time as a way of sort of sampling examples that you feed into this is really fascinating, because this sort of idea means that you're getting a label, you're getting this contrastive label to the system that is coming from some structure of the data, not anything that explicitly you've talked about. It's more of an invariant you expect to happen. Okay, so yeah, this was the paper that first had this, the time contrastive networks, self-supervised learning from video. I think it's a really good paper. It's really changed my sort of interest in this area. So yeah, just in summary, this was a pretty short talk. We talked about supervised learning. That was that idea of fundamentally X to Y, and how we for a lot of the times that's bread and butter, and how transfer is sort of this transfer learning is this idea that we can decompose this mapping into two and reuse the third part. There was this idea of semi-supervised learning. We touched very quickly on that self-training idea of saying that, and that was my little rant where I talked about the idea that I can train a model on a small amount of data, apply that model to an unlabeled data set, and generally get this boost because that idea that as long as the data, the original data, the X comes from the same sort of distribution, then we learn something interesting. And finally, there was this this self-supervised idea, which I think is going to get more and more and more. This idea that we can use these contrastive techniques to learn these encoders that are learnt based on invariance of our data on very, very large labeled data sets, because we don't need any labeled data, and then use those encoders in a transfer learning type way to build very small models on the top of that learned representation. And that was my talk. I hope maybe you got something out of it. See you later.